Welcome to the Simxpert in 3 Dimensions tutorial. In this tutorial you will learn how to create and work with multiple parts, creating and analyzing a 1-dimensional, 2-dimensional and 3-dimensional simple cantilever beam by creating geometry, meshing the model, assigning properties and creating a material, and comparing the results between the 3 different dimensions. Please note the following useful information concerning this tutorial. It should be noted that the introductory tutorial should be completed before attempting this tutorial. Before getting started, it is recommended to check that SI units are being used. These are displayed in the bottom right hand corner and can be changed by double clicking on this area. To create a new part, right click in the model browser window, navigate to part and click create part. Name the part and click OK. Notice the new part is created within the model browser window. We will now create the geometry for a 1-dimensional beam. Notice the geometry tab where all options to create and edit geometries can be found under. In the curve section, select the from points option. This option allows us to create a curve between 2 specified coordinates. We will use the origin as our first coordinate. The beam should have a length of 1 meter in the x direction. Thus the second coordinate should be 1, 0, 0. A 1-dimensional curve representing the beam has been created. Click on Fill to zoom onto the beam. Note that the 3 beams could have been created as one part, but for the purpose of this tutorial, we will create them as 3 separate parts. Therefore, before we can move on to the 2-dimensional beam geometry, we must first create a new part. Make a new part in the same way as previously explained. The planar surface option will be used for the 2-dimensional beam. In the surface section, select the planar option. This option allows us to create a surface within a specified 2-dimensional coordinate system. Select the 1-point method and specify a midpoint coordinate for the plane to be used. The coordinate chosen should be selected so that the surface does not overlap with the 1-dimensional part. Select the XY plane and specify 1 meter for the length in the X direction and 0.04 meters for the width in the Y direction. We have now created the geometry for the 2-dimensional beam. We will now create a 3-dimensional beam. Create another part and repeat the steps for creating the 2-dimensional beam. While changing the midpoint location of the plane to 0.5, 1 and 0. Select the sweep option in the multi-section. This option allows us to extrude any geometry along a vector to create a solid. A vector is created in the same way as a 1-dimensional beam. Create the vector by starting the center point of the surface and extend the vector by any length in the Z direction. The length of the sweep will determine the height of the beam. Hover in the Entities text box until the picking filters appear. Ensure that only the Pick Surface filter is selected, then select the planar surface and click OK. We have now successfully created the geometry for a 3-dimensional beam. We are now going to make a material and assign properties to the 3 geometries. These options are available under the Materials and Properties tab. Select the isotopic option in the Materials section. Name the material Steel and assign the properties as shown. We will now assign inertial and material properties to the 1-dimensional beam. For inertial properties, a cross-section is needed. Therefore, we first have to make a beam cross-section. For this we could enter the values manually, but we will use the beam section library in the 1-dimensional properties section. Select the beam section. For the section type, expand the menu and select the bar option. Rename the section property if you wish. Then change the width of the beam to 0.04 meters and the height of the beam to 0.02 meters. Then click OK. Notice that the property has been created in the model browser. To assign properties to the one-dimensional beam, select the beam option in the 1D properties section. Rename the property and notice under cross-sectional type that a number of options are available. If the beam section cross-section property was not created, then the simple option would be chosen. The area values and second moment of inertia values would have to be inserted manually. For this tutorial, select the library option. For the entities, select the one-dimensional beam. For the material, select steel, and for the section name, select the beam section cross-sectional property previously created using the library. Then click on the Elemental Data tab. The orientation vector of the inertial values cannot be parallel to the beam. Thus specify the vector 0, 0, 1 and then click OK to assign the properties of the one-dimensional beam. Here is a short video which gives a brief explanation of the orientation vector.
If grid points A and B are connected by a bar or beam element, then the element x-axis lies on the line joining points A and B. The beam orientation vector originates from grid point A and is expressed in terms of grid point A's analysis coordinate system. The plane defined by the orientation vector and the x-axis defines the element y-axis. The z-axis is then defined by a right-handed coordinate system. Any vector that lies in the plane will create the same element system, but if either the analysis coordinate frame of grid point A or the orientation vector is modified, then the element coordinate system and the beam orientation may change.
For the two-dimensional beam, select the shell option in the 2D properties section. Rename the property. For the entities, select the 2D beam. For the material, select steel and specify part thickness or height of 0.02 meters. Click OK to assign the property. We have now successfully assigned the property to the two-dimensional beam. Select the solid option under the 3D properties tab to assign the properties to the three-dimensional beam. Rename the property. And for the entities, select the 3D solid. For the material, select the steel. Click OK to assign the property. We have now successfully created the material and assigned properties to all three beams. We will now move on to meshing the geometries. We are meshing the beams after assigning the properties to the beams, as the orientation vector for the one-dimensional beam has to be assigned in the properties before meshing in order to avoid errors later on. All the options needed to create and edit a mesh are available under the Meshing tab. It is recommended to mesh a one-dimensional geometry using the Curve option in the AutoMesh section. Select the Curve option, and for the curve to mesh, select the curve in either the Model Display window or the Model Browser window. Only a linear element type can be used for a curve. For the element property, select the one-dimensional beam property previously created. This holds the orientation vector information for the mesh, which defines the cross-sectional shape of the beam elements. For more information on orientation vectors, see the beam elements section in the Nastran reference manual. In the rendering toolbar, select the detailed rendering option to display the element description in the model display window. To verify that the properties of the one-dimensional beam are correct in orientation and cross-sectional size, compare the model with the three-dimensional beam in the model display window. It can be seen that the two beams are exactly similar, therefore the properties of the one-dimensional beam are correct. We have successfully meshed the one-dimensional beam. For the two-dimensional geometry, the surface option is recommended in the AutoMesh section. Select the surface option, and for the surface to mesh, select the two-dimensional beam. In the element size section, notice that calculate is selected. When this option is checked, Simxpert will automatically calculate the size of the elements. We will overwrite this value and use element size of 1 cm. In the element type section, the default values for mesh type and mesh method are satisfactory for most surfaces. Click OK to create the mesh. We have now successfully meshed the two-dimensional surface. Now we will mesh the 3D beam. For solid geometry, it is recommended to use the solid option in the AutoMesh section. Select the solid option. For the solid to mesh, select the 3D solid. Change the element size to 1 cm, and for the element type, select the quadratic option. It is highly recommended for tetrahedral elements to choose the quadratic elements, since the linear elements will give very large errors in most analyses. Turn off the curvature check option and click OK to create the mesh. We have now successfully meshed all the beams. To view the shell thickness of the 2D beam, click on the drop-down box next to Detailed Element Drawing and select the 3D Shell Thickness option. It can now be seen that the 2D and 3D elements are similar. Click the Detailed Element Drawing button to remove the 3D representation. We will now apply loads and boundary conditions to the beams. To apply loads and boundary conditions, use the options under the LBCs tab. To constrain the beams, we will use the Fixed option under the Constraints section. This option prevents rotation and translation in all directions. Select the entities as shown, meaning for the one-dimensional beam, the leftmost node, the two-dimensional beam, the leftmost curve, and the three-dimensional beam, the leftmost surface. Please note how Simxpert handles the Apply and OK buttons. Pressing Apply will simply assign the selected property. Pressing OK will assign the selected property while also closing the window. Here I have made a common mistake where I've pressed OK and Apply for the last constraint. Hence there are 4 boundary conditions created instead of just 3. Deleting the final constraint solves the problem. To apply force to the beams, select the Force option in the Load section. For the entities, select the nodes as shown in the model display window. After selecting the nodes, change the magnitude to 100 Newton. Change the direction so that the force acts in the negative Z direction to ensure that the force acts downwards on the beam. Select OK to apply the force. When zoomed out, you can verify the constraints are correct and that the force position and direction are also correct. Now create a Nastran job by right-clicking File Set in the model browser and selecting Create New Nastran Job. Rename the job if you wish and ensure the solution type is set to Linear Static Analysis, SOL 101. Save the job in the desired location and click OK to create the job. Now run the job by right-clicking on it in the model browser and selecting Run. When the run has been completed, attach the results XDB file as shown. Under the Results tab, select the Deformation option. Select Translational Displacement. Click Update to view the deformed shape of the beams. Under the Deformation tab, the true and relative displacements can be selected as well as removing the undeformed models. Go back to the Plot Data tab and under the Plot Attributes section, expand the plot type and select Fringe. Ensure that the magnitude deviation is selected and click Update. This allows us to view the magnitudes of the displacements of the beams. It can be seen in the display window that the results correlate quite closely. We have now completed the tutorial for Simxpert in 3 dimensions. Thank you for completing the tutorial. This tutorial was brought to you by ESTEC, Engineering Technology for Better Business.